Chemistry, the Central Science, Chapter 1, Introduction, Matter and Measurement, Lesson 2. So we need to talk about units because units have to be attached to all of the numbers that we're using when we're doing some sort of measurement. A number without a unit is pointless. So here's our basic standard units within the metric system. So length is meter. Mass is kilogram, time is second, electric current is the ampere. Temperature is Kelvin. Notice that's not degrees Celsius or degrees Fahrenheit. Your amount of substance is mole. And I want you to pay attention to your symbol for mole is MOL, not M, right? M represents a meter. So when we're doing conversions, we always want to make sure we're using the right symbol. And then luminous intensity is the candela. So the prefixes that are used within the metric system tell you what factor of 10 are they based off of your standard unit. You'll see here that typically, with the exception of the kilo, anytime you have your prefix ending in I or O, it's going to be a much smaller unit. Things that end in an A, like mega, giga, and tera, are going to be really large. So in looking at this, what does this mean? A kilogram is 1,000 grams. A megagram is 1 million grams, etc. A decigram is 1/10 of a gram. A centigram is 1/100th of a gram. Another way to look at these smaller units is to say there's 10 decimeters in 1 meter, or 100 centimeters in a meter, or 1,000 milliliters in 1 liter. So you just need to pay attention when you're doing these conversions to think about where you're placing the exponent or the factor of 10 and the exponent itself, whether it's positive or negative. So measuring mass and length, right? Mass is the amount of substance that is present. So how much stuff do you have? It is not the same as weight. Weight is dependent upon gravity. So mass times gravity tells you how much something weighs. So we weigh differently here on Earth versus on the moon. However, our mass is constant. That is fixed because you're not losing any of your substance. And length, of course, measures a distance, and that is measured in meters, whereas our mass are typically, well, in the lab, we're going to measure it in grams, but if you were to weigh yourself, you would weigh yourself in kilograms. So the temperature scales, we have Kelvin, Celsius, and Fahrenheit. Kelvin is the absolute temperature scale. It is based off of gas behavior. Lord Kelvin came up with this when he was studying different pressures of gases, he would study gases. They would all be at the same pressure, and he would look at how do the volume and the temperature of these gases correlate. And extrapolating data, he saw that no matter what the pressure was, the volume and temperature, the temperature would always go to a specific point, and that specific point was considered to be absolute zero. So that is why the Kelvin unit does not have a degree symbol in front of it, because it is absolute. Your degrees Celsius and degrees Fahrenheit are based off of the behavior of water, specifically looking at what temperature does water freeze and what temperature does water boil. Over here, we have our equations that tell us how can we convert in between units of temperature. So here, if you have degrees Celsius, you simply add 273.15. That's how you get to Kelvin. Vice versa, if you had Kelvin, you would subtract 273.15. If we want to solve for degrees Fahrenheit and we're given degrees Celsius, we're going to plug in our temperature for Celsius here, multiply by 9/5, which is the same as 1.8, and then add 32. So we keep in mind that we do the multiplication first, and then we add 32. If instead we're given degrees Fahrenheit and we want to get to degrees Celsius, we're going to plug in our temperature for Fahrenheit here. Now we have to do what's in the parentheses first. We will subtract 32 and then multiply by 5/9. If you look at these equations, you can see that they have just been rearranged from each other. I like to keep things simple, so If I'm given degrees Celsius, I'm going to use this equation to find my Fahrenheit. Or if I'm given Fahrenheit, I want to use this equation to find my Celsius so that I don't have to do the rearranging as I do the math. You'll also notice that there is no direct calculation to go between degrees Fahrenheit and Kelvin. So you're always going to have to take a pit stop in the land of degrees Celsius to get there. Here's just some standard temperatures, right, for which water boils and freezes. So water freezes at 0 degrees Celsius, which is the same as 273 Kelvin, boils at 100 degrees Celsius, which is the same as 373 Kelvin. And then we see that that boiling temperature corresponds to 212 degrees Fahrenheit, and the freezing point corresponds to 32 degrees Fahrenheit. So in the land of chemistry, we aren't going to be using degrees Fahrenheit. We live with the land of Celsius. And then in certain equations, we're going to have to use absolute temperature values. So volume is representing how much space an object occupies. So here we can take a look at some metric units and what their correlations are. A centimeter cubed, and this conversion here is important because anytime you're converting a unit that has an exponent, a power to it, the factor by which you're converting also has to be raised to that same power. So what this is saying is there's effectively 100 centimeters in 1 meter, or a meter is 1/100th of a centimeter. So that's what this 1 times 10 to the negative 2 means. We multiply our exponents, and we see that 1 centimeter cubed is the same as 1 times 10 to the negative 6 meters cubed, or 1/1,000,000th. A decimeter cubed is the same as 1/10 of a meter cubed. So there's 10 decimeters in 1 meter. So once again, we multiply our exponents, and we see that a decimeter cubed is the same as 1 times 10 to the negative 3rd meter cubed, or 1/1000th meter cubed. A decimeter cubed is actually the same as a liter. So that is a direct correlation there. We also know that 1 liter is 1,000 milliliters. 1 milliliter is also equal to a centimeter cubed. So anytime you see a milliliter, you can kind of just replace it with the centimeter cubed because there is a 1-to-1 relationship here. That allows us then to convert between solids, which we would measure if it was a regular solid, right, where it's a cube, a perfect cube. We measure length, width, and height to get to a volume. Well, when you're measuring lengths, you have to use a unit of length, which would be a centimeter. You cannot measure length in milliliters or liters. But then this allows us to convert between milliliters and centimeters cubed to say, oh, this is the same volume as this particular amount of liquid. So milliliters and liters are going to be your unit that is associated with a liquid. So density is an intensive property because it does not depend on how much of the substance that you have. It is part of its identity. So if you have a 10-gram block of gold, you have a 100-gram block of gold, gold is still gold. The density of both of those would be the same. However, the extensive property of their masses are clearly different. So density is a ratio of a substance's mass compared to its volume. You can use any type of units here. You just have to make sure that whatever your units of mass and volume are going to match the units that would be given in density. Here I give you what I call the density triangle, which is a simple way to remember how to use this equation. So what these lines mean here, I have M over V. So anytime I have a vertical line, that means I'm going to divide, or sorry, a horizontal line, I'm going to be dividing whatever's on the top by what's on the bottom. So if I want to find density, that means I take mass divided by volume. My vertical line is going to mean that whatever's next to each other, I would multiply together. So for example, if I was asked to find the mass, I know that I have to multiply density times volume. And lastly, if I wanted to find volume, I'm going to take the mass and divide it by the density. So this is how this little triangle works. You kind of cover up what you need and you see what is the relationship between my other two variables. So a piece of platinum metal with a density of 24.8 grams per centimeter cubed has a volume of 5.31 centimeters cubed. What is its mass? So when we start to do problem solving, I like to pull information out. So this question is giving me information and it's asking me to find something else. What's giving me is that I have a density. So I would record what my density is, 24.8 grams per centimeter cubed. I'm also told that I have a volume of 5.31 centimeters cubed. Those are my given pieces of information. I'm asked to find the mass. Now, before I do any math, we always want to make sure we have the correct equation. So we have our density equation. We also want to pay attention to our units. And right, this is just the rearranged equation, which we can, of course, get from our triangle. If we cover up the m, that shows d next to v, so I multiply. In this, I notice that my units of volume are the same. They have to be the same in order for them to be able to be canceled out. If, for example, your volume was given in meters cubed, we would have to do a conversion to get back to centimeters cubed. So multiplying these two values together, I get a number. And with rounding, I report to 3 significant figures because there's 1, 2, 3 here, and there's 1, 2, 3 here. And I'll talk sig fig rules here in a minute. So what is the mass of this volume of platinum? 132 grams. Now, densities are always going to be listed with a corresponding temperature. Why? Well, when we think about density, we see that it is a mass to volume. Well, volume can change based on temperature. Substances can expand or contract based on how hot or cool they are. So water changes density. As it freezes, it starts to, around 4 degrees Celsius, it actually starts to expand, which is quite odd because most substances, when they get colder, they contract. So water is very special in that aspect. So all densities are going to be listed with a temperature because the volume can be changed based on temperature. So basically, your density can change based on temperature. So 2 important things in values or in measurements that we're going to take, and we want to be both precise and accurate. So precision is looking at how close are your measured values to each other. Accuracy is how close are your measured values to the true value. So for example, we're throwing paper balls into this trash can. So we made them all in, we scored all our points, good accuracy, good precision. Here we notice we didn't make any of them in, but they're all grouped together. So this says, I didn't hit my target, but all my values were close together. This is good precision. This could mean that perhaps your measuring device needed to be recalibrated. Perhaps your balance is not right or your thermometer is not reading correctly. We would want to recalibrate it. And the last one, clearly nobody did a good job here. We missed our target and we're all over the place. So we have poor accuracy and poor precision. Significant figures, which I'm sure is everybody's favorite. So let's take a look at these numbers and identify how many significant figures we have and what rules we can gain from this discussion. So my first number, 1.234 kilograms, that has 4 significant figures because rule number 1 says all non-zero digits are always significant. And it does not matter where the decimal point is. If this was 1,234 kilograms, it still has 4 sig figs. And 606 meters, there are 3 significant figures because that is what I like to call the zero sandwich rule. So anytime zeros are sandwiched between any non-zero digits, those zeros are always significant. In 0.08 liters, there is only 1 significant figure because leading zeros do not matter. So we ignore those. Those are just holding a place for us. So we ignore any leading zeros. They do not matter. 2.0 milligrams. Here, instead of having zeros in front of a number, we have zeros both behind a non-zero digit and behind a decimal point. So this is my to the right rule. Any zero to the right of a number and to the right of a decimal point will always be significant. And this does not matter because if we look down at 0.00420, we notice that our non-zero digits come after the decimal point. That doesn't matter. That 0 at the end is still significant because it's both to the right of a non-zero digit and to the right of a decimal point. And lastly, we have here this 95,000 seconds. Well, here this number is considered to be ambiguous because we don't know whether these zeros were significant. Was this measured to be exactly 95,000 seconds, or was this number rounded? So we know for sure that the 95, those two digits are significant. So there's at least two sig figs. After that, we do not know whether these zeros matter or not. So a correct answer here could be there's 2, there's 3, there's 4, there's 5 sig figs. We don't know. That is why putting numbers into scientific notation is very beneficial because that will tell us exactly how many significant figures we have. Other things to talk about with numbers. So we have exact numbers and inexact numbers. Exact, not inexact. Exact numbers are any type of counting number. So this is especially important when we're looking at a number of trials and we want to take an average. The number of trials that you do, that is a counting number. Exact numbers are considered to have an infinite number of zeros after it. So infinite number of sig figs, which means that one would never be counted in your significant figure calculation rules. Inexact numbers are any type of measurement that you make. So these are the numbers that have grams or meters or degrees Celsius or liters or whatever after it. All measured numbers are considered to be inexact because it depends upon your measuring device. How many places past the decimal point does your measuring device go? That last digit is always going to be an uncertain digit. So we have 3 measured masses. What do we have here? If we want to find the average, well, we add up our numbers, we divide by 3. We notice that we get a number your calculator is going to spit out at you. How many sig figs should we have in our final answer? Well, we have 3, 3, 3, so our final answer has to have 3. We do not round to 8, okay? We cannot have a measured average that is larger than any one of our individual values. This would not make sense. So 3 is an exact number. Another thing I want to point out, when we do dimensional analysis, aka unit conversions, we treat all of our conversion factors as if they are exact numbers. So those would never be values that you would consider in your multiplication and division in determining the number of significant figures you have at the end. We're always going to start with our measured value. That's the number that we're concerned with. That's the one that we count our sig figs. That's the one that determines our final answer. So calculations then, making sure we pay attention to our significant figure rules. Addition and subtraction, same rule. The answer cannot have more digits to the right of the decimal point than any of the original numbers. So basically what this is saying is I can add up my numbers. That's fine, put it in your calculator. So now what I want to do is I just ignore what's in the front of the decimal point and I count. There's 1, 2, 3 sig figs here. There's 1 here. 1 is less than 3. So I can only have 1 place past the decimal point, which means I round to 90.4. Same thing with subtraction. I put this in my calculator, I get a number. Here I have 2 places past the decimal point. Here I have 4 places past the decimal point. So 2 wins over 4, which means my final answer can only have 2 significant figures. I look here, that would be my 0.78. My 6 will round my 8 up to be 0.79. Multiplication and division is a little bit different. So now we actually are just going to count all of the numbers that are there, determine which has the smallest number of significant figures. So whether it's in front of the decimal point or after the decimal point, we care about all of them. 4.51 has 3 sig figs. 3.6666 has 5. 3 is less than 5. We put this in our calculator, we get a number. We go off of our smallest number of significant figures, so we round to 3, which is my 16.5. I look at what does the 3 do to the 5? Well, it's not going to do anything to it, so 16.5 is my answer. Division. Put this in your calculator. Spits out a number. 2 sig figs, 5 sig figs. So my final answer can only have 2 significant figures. We might be tempted to say, oh, that's my 0 and 6, so this must round to 0.06. However, we have to remember that leading zeros are not considered to be significant. So what we're concerned with here is then the 6, 0. What does this 6 do to this 0? Well, it's going to round it up. So my final answer will be 0.061. Lastly, but actually most importantly, we're going to talk here about dimensional analysis, which is just a fancy way to say, how do we convert from one unit to another? This is going to come up time and time again, so I cannot stress enough how important it is to understand how to do this now. We want to identify what we're given and what we want to get to, so our givens and our wants. Once you know that, there's a list of conversion factors in your book that will tell you this many, there's 2.54 centimeters in an inch, or there's 1,000 meters in a kilometer. That is your conversion factor. We carry our units through the calculation, and we want to make sure the units that we start with will cancel. So your given quantity, you're going to multiply by a conversion factor to get to what your desired quantity is. The way that this works out, I like to set up what I call picket fences. There are other ways to do this, whatever works for you, as long as you can get to the right answer and show your work, I'm totally cool with it. So when we do this like this, we know that what we start with and we multiply by this conversion factor, your given unit has to be on the bottom so that there is this diagonal relationship. I like to call this, right? It's next door downstairs. The unit here has to be the unit here. Your conversion factors do not change your measurement. It's just representing it in a different way. So how many milliliters are in 4.19 liters? Well, my given information, 4.19 liters. I want to get to milliliters. So that means I need to find my conversion unit. Well, 1 liter is 1,000 milliliters. I will start by writing down my given information. I always start with this here. And this is over an imaginary 1, right? Anything divided by 1 is itself. So I need to make sure I match up. Liters are here, liters have to be here. I put my 1,000 milliliters on the top, and then I notice that my liters will cancel. I end up with 4,190 milliliters. This 0 here is ambiguous. We'll talk in a minute about scientific notation. If we wanted to represent this number accurately, we would say 4.19 times 10 to the third milliliters. Now, what if we don't set up our conversion factor correctly? We will notice here that liters and liters are on top. That would give me a liter squared in the end. My milliliters are on the bottom, so that nothing is going to cancel out. I end up with some weird unit of liters squared over milliliters, which makes no sense whatsoever. So this is just making sure that your units that you start with, whatever it is, has to go next door downstairs. So what if we have a compound unit? The speed of sound in air is about 343 meters per second. What is this speed in miles per hour? So once again, identify that this is my given information, 300, excuse me, 343 meters per second. What do I want to find? Well, I need to find miles per hour. So I need to know that I'm going to be converting meters into miles because those are my two distances, and seconds into hours because those are my two time values. So what are the conversion units I need? I look this up in my book. 1 mile is 1,609 meters. I know that there are 60 seconds in a minute, and I know that there are 60 minutes in an hour. Once again, I start with my given information. Anytime you read something and you say, something per something else. Meters per second, grams per milliliter, kilograms per cubic kilometers. These are all meaning that this unit is on the top and this unit is on the bottom. So we would not put M/S, have that be a compound unit on the top. If you do that, you're going to mess up your calculation. So I can get rid of my meters by this conversion factor here, meters, meters. Those are diagonally to each other. I have my 1 mile on the top. Now, I need to get rid of my seconds. Well, now instead of a next door downstairs, I have like 2 neighbors down the hallway upstairs. Why? Because this unit is on the bottom. You have to have a diagonal relationship between your units in order for them to cancel out. That is the bottom line. So to cancel out my seconds, I'm going to use my conversion factor of seconds to minutes. And then to cancel out my minutes, I'm going to use my conversion factor of minutes to hours. So the math that I'm going to do is I multiply everything together on the top. 343 times 1 times 60 times 60. Calculator gives me a number. I do not round anything. I save it as it is. Divided by, parentheses, 1609 times 1 times 1. Your calculator gives you a number. We are going to round to the number of significant figures that is in our given value. There are 3 sig figs here. There are 3 sig figs here. So what this means is 343 meters per second is the same speed as 767 miles per hour. And we notice that we did this calculation correctly because all of the units that we did not want to have in our final answer were canceled out. We're left with, right, our miles on the top and our hours on the bottom. This is why it is so important when you do these conversion factors to write your unit along with your number. If you just write down numbers, you're going to get to the end and you're going to have a number, but you're not going to know if you actually have the correct number or the correct unit. So it can be tedious, but this is part of bookkeeping in chemistry, is making sure that your numbers always have a unit with them. All right, and just a little note about scientific notation. The book, I didn't see that it really talks about it, but we need to discuss it. So the number of atoms in 12 grams of carbon is a boatload, right? And we don't want to have to write out all these zeros all the time. That's just, nobody has time for that. So we're going to convert this number to represent it as a factor of 10. The mass of a single carbon atom in grams is a really teeny tiny number. Nobody wants to write out all those zeros either. So once again, we can represent extremely small numbers as a factor of 10. Notice here that when we have a large number, our exponent is positive. When we have a small number, our exponent is negative. And these are in relationship to each other, these particular values here. So scientific notation says I have to have a number times 10 to another number. Your number that goes in the front is between 1 and 10. Not 10, but between 1 and 10. If this number was 10, we know we could move our decimal point one more place. And your exponent is either positive or negative, and it's always an integer. So how can we put this number into scientific notation? Well, I noticed that this number is a large number, 568.762. So in order to get this to be a number between 1 and 10, I move my decimal point to the left. I moved it 2 places. So my exponent then is the number of places I move my decimal point, and it's positive once again because my number itself is a large number. Here, I notice all these leading zeros, which of course are not significant. So this tells me I'm a small number. My exponent's going to be negative. I need to find a number between 1 and 10. So I have to move my decimal point 1, 2, 3, 4, 5, 6 places so that it is 7.72. That is a number between 1 and 10. I'm not going to have 77.2 because that's not right. So I move my decimal point to the right, It is a negative number as my exponent because my number is small. It is a fraction, right? So what do I do with numbers in scientific notation when I have to add or subtract them? The important thing with addition and subtraction is that your exponents have to be the same value. If they're not, that means that your decimal point is not in the same place. We know in addition and subtraction, you have to line up your decimal points to get to the right value. So there might have to be some converting that you do. Once you do this, you simply are going to combine your n values, right? The numbers that come before your factor of 10. And then you're going to leave your n, your exponent, little n, the same. So in trying to add these two numbers, I noticed that my exponents are not the same, which means I have to change one of these. It doesn't matter which ones you change. You just pick one and go with it. So I could make this value 43.1 times 10 to the third, or I can make this value 0.39 times 10 to the fourth. So we chose the latter option. So now that my exponents are the same, I simply add 4.31 to 0.39. I end up with 4.70. I keep my exponent the same, so my final answer is 4.70 times 10 to the fourth. Notice, in addition, we are looking at the number of places past the decimal point. I have 2 places here. I have 2 places here. So that means my final answer has to have 2 places past the decimal point to pay attention to our significant figure rules. And then what do we do with multiplication and or division? With multiplication, you're just going to multiply your numbers together. We do not care what the exponents are on our factor of 10 because you're just going to add them, whatever they might be. And then we would do any type of rounding. So I have 4.0 times 7.0, right? That gives me 28. I have -5 plus 3, which gives me -2. So sig fig rules tells me 2 sig figs here, 2 sig figs here, right? Because these zeros matter. They are to the right, to the right, to the right of a number, to the right of a decimal point. So that means my final answer can only have 2 sig figs. So it's simply 28 times 10 to the -2. Now, this is not a way to leave our number in scientific notation because this is not a number between 1 and 10. So we simply move our decimal point to the left. And that is going to change our value then to 2.8 times 10 to the -1. How did we get that? Because if we've moved it to the left, we know that that would mean multiplying by a factor of 10. So 10 to the first power times 10 to the -2nd power gives us a 10 to the -1 power. In division, it's similar to multiplication in the fact that you're just going to divide your numbers, your big N's. Now, instead of adding your exponents, you're going to subtract your exponents. And it's the exponent on the top, you subtract away the exponent on the bottom. So 8.5 times 10 to the fourth divided by 5.0 times 10 to the ninth. We can do the math of 8.5 divided by 5. Calculator gives you a number. 10 to the fourth divided by 10 to the ninth means 4 minus 9. So we end up with a final answer of 1.7 times 10 to the -5th. Here, 2 sig figs, 2 sig figs, 2 sig figs. Anytime you're looking at scientific notation and determining significant figures, these exponential values here mean nothing. This just tells us where the decimal point is. So we do not pay attention to that. Does not affect significant figures. And anytime your value is represented in scientific notation, however many numbers are represented in the front here by your big N, that tells you right away, this is how many sig figs I have. You don't even have to worry about counting them.